Let's take a look at what this problem is saying. So it's a 0.40 kilogram ball, and it's suspended from a spring with a spring constant of 12 newtons per meter. And it turns out that's a pretty heavy ball. 0.4 kilograms is something like a pound. 12 newtons per meter. A pound is about 5 newtons, and that's how much restoring force it provides if it's stretched by a distance of 1 meter. So that's a pretty gentle spring, and it's a reasonably heavy mass. And so we're expecting this thing to oscillate up and down pretty gently. And as a consequence, I'm expecting the maximum speed while it oscillates to not be all that great. But that's what the problem asks about. You take this ball, you suspend it from a spring, you pull it down by 0.20 meters, let it oscillate. What is the maximum speed? So the ball sits like this. I pull it down by a distance of 0.20 meters. So I'm holding it here, I let it go, the ball moves upward, passes through its equilibrium position, so it starts out here, moves upward, passes through its equilibrium position right here, continues to move upward, and then kind of ends up at its highest point right here. We end up with something like that. So you let the ball go, goes through equilibrium position, ends up here. Question, what is its maximum speed? And of course the maximum speed happens right when it's at the equilibrium position. I want to know what V max is. What is the maximum speed right there? And I expect this to be a pretty chill oscillation. As I'm saying, this is a pretty gentle spring. It's a reasonably heavy ball. So I'm expecting it to be pretty chill maximum speed. But we have an expression for the maximum speed, and it just looks like this. The maximum speed for a mass on a spring, or for any simple harmonic oscillator, is this. It's just 2 pi times the frequency times the amplitude. So all we have to do is we have to extract from the problem statement the details necessary to solve this equation. Well, the amplitude is this. I pulled it down by 0.20 meters, so it's 0.20 from its equilibrium position. That is just equal to the amplitude. So the amplitude is 0.20 meters. Okay, because that's how far I've displaced it from equilibrium. So I know amplitude in this equation is 0.20 meters. The frequency, we have an expression for the frequency. For a mass on a spring, the frequency is just equal to 1 over 2 pi times the square root of k over m. And I'm given k, it's 12 newtons per meter, and I'm given m, it's 0.40 kilograms. And so I can solve for the frequency. If I do that, I get this, 0.872 hertz. This is a little bit less than once per second. And so that seems like a gentle oscillation, which in fact is what we're expecting. Our solution then looks like this. It's pretty straightforward. The maximum speed is just equal to 2 pi times f times a. The amplitude is 0.2. The frequency is 0.872. I have everything I need to solve. And if I do that, I get 1.1 meters per second. Well, 1.1 meters per second is about 2 miles per hour, okay, which is a rather gentle walking speed. So I've taken this mass and I've pulled it down by 20 centimeters, and it's oscillating up and down less than once per second. I expected this speed to be pretty low, and in fact, that's what I find. And so as our final step, we look back and we assess, and we say, at the end of the day, this problem answer matches our initial prediction. The problem solution matches how the world works, and that's the thing we check for last when we solve any problem.